this example, we have a data set of points. In this case, it's actually 3 points, and we are going to find out the line, the equation of the line that crosses this data set of points. Okay, so for this, we are going to use the gradient descent. The gradient descent is a iterative method in which the parameters are optimally determined in small steps, starting from an initial solution. In this case, this initial solution is the slope equal with 1 and the intercept equal with 0. We know that the equation of the line is y equal with slope multiplied by x plus the intercept. So the problem is formulated like this: we must optimally determine the slope and the intercept of the line so that the sum of the square residuals is minimized. Okay, so what that means, let's put here 1 just to see the line of slope 1 and intercept 0. Okay, so this is the line, the starting point of the problem. Okay, so the sum of the square residual means the distance between this point and the line square plus the distance between the line and this point square plus the distance between this point and the line squared. So we're going to minimize these sums. Okay, so for this we're going to use the gradient descent as I mentioned, and the algorithm starts with this loop in which we are going to compute the loss function, I mean the sum of square residuals, starting from an initial solution. Yeah, our initial solution, or an estimated solution, which is 1 and 0. 1 meaning slope 1 and 0 meaning intercept 0. Okay, then the Jacobian is going to be computed with this script, in which the input of the Jacobian script is going to be the loss function, I mean the sum of the square residuals equation, and the estimated solution of slope 1 and intercept 0. And the output of the Jacobian is going to be actually is going to be a matrix with 2 elements inside. First element is going to be the derivative of the loss function with respect to the slope, and the other is going to be the derivative of the loss function with respect to the intercept. Yeah, something, yeah, let's see inside. Yeah, something like this. Yeah, this is just for the first iteration. Okay, obtaining these values from the Jacobian, we are going to multiply these two values that we obtain from the Jacobian with the learning rate. Learning rate is going to be, yeah, a small value. Yeah, and then we are going to subtract these values from the initial slope, the previous slope, yeah, in this case initial slope, and the initial intercept. Yeah, here the solution the estimated solution is going to be updated. Here the plot is going to be constructed, the points and the equation of the line, and the process is repeated until the number of equation is met, or the difference between the loss function of from current iteration is going to be smaller. The difference between the current loss function and the loss function from the previous iteration is going to be smaller than epsilon. Okay, so let's see. So when we are going to run the algorithm, we are going to see that the line is going to move up. Yeah, is going to center itself with every small step. So let's see. Yeah, we can see that it's going up. At the beginning, the line was exactly passing throughout 0. Now is going up with every iteration. We can see here some information, that the iteration number, the loss function value, epsilon, the slope, and the intercept. These are the solution. Yeah, and in the end we are going to see what we are going to obtain. Okay, so we reached 200 iteration as we defined at the beginning. Okay, so this is what we obtain. We can see that our equation, our line is now optimally passing throughout this data set of points, and the equation of the line is y equal with 0.68 multiplied by x plus 0.85 in this case. So we are going to see, yeah, this is the equation of the line. Yeah. Okay, to compare the result, we're going to see other example of mine in which we are going to use the least square method. Okay, let's find where that example is. Meta heuristics, data fitting. Okay, so select data is 6. In that matrix, yeah, data 6 are those 3 points that we defined earlier in the example. Okay, and actually here we can fit any kind of polynomial, yeah, inside this data, inside any data set. Yeah, but in this case we are going to use the degree of the polynomial 1, meaning the equation of the line, exactly like the previous example. Okay, so let's see what how it works. Actually the optimal solution is when the derivative of the error with respect to coefficient a is equal with 0, and the derivative of the error with respect to b is equal with 0. So when these two equations are solved, we're going to obtain a, meaning the slope, and b, meaning the intercept. Okay, so let's run the algorithm. It's very simple. You can see the points here and the line exactly like the previous example, but the optimal value are 0.64, 0.94, almost the same like the previous example. But if in the previous example we put more iteration, we will obtain also these values. Okay, thank you.